Hello good people, I'm going to talk about isotopes and the average atomic mass. So firstly, what are isotopes? Isotopes are atoms that differ in the number of neutrons. Or another way to put it is to say that isotopes of an element have the same number of protons but a different number of neutrons. What does this mean? Well, let's look at three versions or three isotopes of hydrogen. So here are three nuclei. Each has only one proton. Recall that it is the number of protons that determines the identity of the atom. So in these three cases, each nucleus has only one proton, which means that in each case, I'm dealing with an atom of hydrogen. How do the nuclei differ? Well, the difference is in the number of neutrons. In case of the nucleus on the left, I have 0 neutrons. When it comes to the middle nucleus, I have 1 neutron. And when it comes to the nucleus on the right, I have 2 neutrons. So these are the three isotopes of hydrogen. Atomic symbols can be used to distinguish between different isotopes. So for all three of these hydrogens, the chemical symbol would be a capital H. For all three, the atomic number, or the number of protons in the nucleus, is 1. What about the atomic mass number? Well, this will be now different. Remember, the atomic mass number equals number of protons plus the number of neutrons. So in case of the hydrogen on the left, the atomic mass number is 1, because I have 1 plus 0. In case of the hydrogen in the middle, the atomic mass number is 2. 1 proton plus 1 neutron. And in case of the hydrogen on the right, the atomic mass number is 3, because now I have 1 proton plus 2 neutrons. In terms of language, we distinguish between different isotopes by indicating their atomic mass number. So the hydrogen on the left will be known as hydrogen 1. The hydrogen in the middle will be known as hydrogen 2, and the hydrogen on the right will be known as hydrogen 3. As it so happens, hydrogen 2 and hydrogen 3 also have their own special names. So hydrogen 2 is known as deuterium, and hydrogen 3 is also known as tritium. Although all three of these isotopes can, and in fact do exist, they do not exist in the same amount. Most of the naturally occurring hydrogen exists as hydrogen 1. In fact, 99.97% of all hydrogens are hydrogen 1. About 0.02% of all hydrogen atoms are hydrogen 2, and the rest is made up of hydrogen 3 or tritium. The relative abundance of each isotope will influence the average atomic mass. And that is what I want to explore next. So let me get rid of this, like so, and the first thing I want to do is define the average atomic mass. So the average atomic mass is the sum of all isotope masses with respect to the natural abundance of given isotopes. Well, that's a lot of words. Maybe a nice mathematical formula will help. So I could say the average atomic mass equals the sum of the atomic mass of one isotope multiplied by the proportion of that isotope plus the atomic mass of the second isotope multiplied by the proportion of the second isotope plus the mass of the third isotope multiplied by the proportion of the third isotope, and so on. Now, before you go screaming into a pillow, let's unpack this formula. Firstly, this symbol here is the capital Greek letter sigma. It stands for sum of, and it indicates that I need to add all of the following terms together. So in this particular case, I have m1 times p1 that I will add to m2 times p2, that I will add to m3 times p3, and so on. The n terms stand for the atomic mass. And the p terms, they stand for the proportion of the isotope. So how does all of this work together? Well, let's look at an example. Boron has two naturally occurring isotopes. So I'm going to bring in those nuclei. On the left, I have boron 10. The atomic symbol for boron 10 would be B, and then 5 for the atomic number, and 10 for the atomic mass. And it so happens that about 19.90% of all boron atoms are boron 10. On the right, I have boron 11. The atomic symbol for boron 11 would be capital B. The atomic number is 5 because I still have 5 protons. And the atomic mass would be 11 because now I have 6 neutrons. 5 plus 6 is 11. And it turns out that about 80.10% of all boron atoms are in fact boron 11. So what is the average atomic mass of boron? Well, I'm going to apply the formula above. So firstly, I'm going to write average atomic mass equals the atomic mass of the first boron isotope, which happens to be 10. So I'm going to write 10 AMU. Remember, AMU stands for atomic mass units, multiplied by the proportion of boron 10. Here you have to be a little bit careful. I need to multiply by the proportion, not the percentage. The way to express a percentage as a proportion is to simply divide it by 100. So 19.9% divided by 100 is 0.1990. So this takes care of boron 10. To that, I'm going to add the mass and the proportion of boron 11. The atomic mass of boron 11 is 11 AMU, and I'm going to multiply that by the proportion of boron 11. The percentage is 80.10%, which means the proportion is 0.8010. And now I'm going to use my calculator. And here it is. Let me just move it out of the way so I can see my numbers. So I have 10 multiplied by 0.1990 plus 11 multiplied by 0.8010. And I get 10.801. So I can say that the average atomic mass of boron is 10.801 AMU. Now, depending on your periodic table of elements, the average atomic mass for boron might be given as 10.811 or possibly 10.8. Why is that? Well, it depends on the way the average atomic mass was calculated. Or more precisely, it depends on these percentages. So this 19.9% abundance for boron 10 might not be exactly accurate. Maybe it's 19.903, or maybe it was 19.87 that was rounded up. So there will be small discrepancies. So it is a good practice to pick one periodic table of elements and stick to the values that are provided by it. Or alternatively, if you are solving a problem, use the average atomic masses that are given to you by that problem. We will explore that in later videos too. In summary, isotopes are atoms that have the same number of protons but different number of neutrons. And the average atomic mass is calculated by taking into account the masses of those isotopes and their relative abundance. That is all for now, and I will see you on the flip side.